All right, Chapter 12, Section 6, Proving Triangle Congruence by ASA and AAS. So we're wrapping up our unit on triangle congruence with our last two theorems that we're going to be dealing with how to prove that two triangles are congruent to each other. And so again, this is all based around this concept that when two triangles are congruent, triangles specifically, they have 6 elements in common. All 3 angles, corresponding angles, will be congruent to all 3 corresponding angles in some other triangle. And all 3 side lengths will be congruent to all 3 side lengths of the other triangle. So that's 6 elements in total. And in section 2, we talked about how with congruence statements, we would have to list out all those items, all 6 things to be shown to be the same between two triangles specifically. And the more complex the figure that it gets, like a quadrilateral, now we have 8 elements. For a pentagon, now there are 10 elements, and so on and so forth. That's a lot of things to show are congruent to a lot of other corresponding things. And so what this unit is about what's the minimum amount of information I can have to show that the two objects are congruent to each other, and then all the other things have to fall into place without me going through the process of measuring them or showing that they're the same. Okay, and so we'll do a little review in this section about the various ways that we can show triangle congruence. For right now, let's just focus on the two in front of us, ASA and AAS. The punchline here is this marginal note, is that basically if any 2 angles and any one side of 2 triangles are congruent to each other, then the triangles have to be congruent. Okay, so any 2 angles and any given side. Right? And the reason why I have 2 different names for this, angle, side, angle, and angle, angle, side, again, this just breaks down the order in which you see it. So if I have 2 angles and any given side, if the side happens to be sandwiched between those 2 angles, like these, angle, angle, and then the side is the side that connects those 2 angles, that's what we would call ASA, angle, side, angle. If it's any other leg, so angle, angle, side, side, angle, angle, it doesn't matter. If I have 2 angles and a side, it's AAS. If the side happens to be sandwiched between the 2 angles, then I would just call it ASA. It's a minor difference, but it's important to keep that order because this is a recall back to section 3 when we talked about SAS, where I have 2 sides and the included angle, the angle sandwiched between them. So the actual acronym itself, the order of the letters ends up mattering. Okay. And yes, just to point it out again, it is unfortunate, but there is no ASS theorem. I was disappointed too when I was in high school that there is no AS theorem, and I apologize that math is even boring enough to not have a proper dirty word acronym. I apologize. Anyway, but for these 2, this is what we need. 2 angles in a given side, and just the order in which you spot it is just the only distinction between ASA and AAS. So let's do a little review here in the margin before we jump into this last one of our last examples. How can I prove triangle congruence? These are the various ways in the margin, and this is worth writing down and annotating. These are the various ways I can show the 2 triangles are congruent to each other. The first way listed right here is the long way to do it. Okay, if all 3 corresponding angles and all 3 corresponding sides are congruent, then the 2 triangles will be congruent to each other. Okay, that's basically all the information. And if I have to go through the process of measuring every side and measuring every angle, that's a lot of work. But that's one of the ways that I can show triangle congruence. It definitely works. And then these ways are the shortcut ways. We talked about SAS first. That was in section 3, side, angle, side. The one stipulation here was that the angle had to be in what's called an included angle, or the angle that's sandwiched between 2 sides. Okay, and so that was in section 3. If I can show that those 3 pieces of one triangle are congruent to the other 3 pieces in another, then I don't have to go through the process of finding the other pieces of information. Okay. Then we talked about side, 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 and the offshoot of that being the HL theorem, or the hypotenuse leg theorem. That was in section 5 that we talked about these two. And so in these cases, I have no information about the angles, but if I can show all three sides are congruent to all three sides of another, then they have to be congruent. The hypotenuse leg theorem, just like this little note says, this only works for right triangles. And for the hypotenuse leg theorem, it's an offshoot of side because now I only need two sides, the hypotenuse specifically, and one of the legs. Okay, the hypotenuse and one of the legs. So if I can show a hypotenuse and a leg of a right triangle is congruent to a hypotenuse and a leg of another right triangle, then all the other things fall into place. And then in this section now, section 6, ASA and AAS, basically if I get any two angles and a side, it's going to be one of these two. It just matters with the order. Just be aware of that. That's the only distinction between these two. But again, it's limited information that allows me to extrapolate out to larger pieces of information. It cuts my work down in half, and that's always an important thing to do. One thing to notice about each of these theorems is that I need some side in one shape or another, right? In this one, I only have one side in common with the other. The reason why I don't have an AAA theorem is because the AAA would only refer to the angles, which means I could have two completely different sized triangles. I could have a triangle, say like this size, where it's like the size of a finger. But then I could take this same triangle and blow it up, zoom out, to zoom in on to the point where maybe it's miles long, but it would have the same angles, because angles don't really care about how far zoomed in or zoomed out you are. So the reason we don't have an AAA theorem is because a side length locks in the actual scale of that triangle. Okay, and that's something that we'll explore a little bit more in math too, the concept of what we call dilation or scale factor. And that's something you probably can kind of inherently understand. But anyway, that's why we don't have one for triangle congruence. Again, congruence means that it is the exact same copy and paste triangle as the other. All right, so this example here ends up being a pretty important one in this unit. This is arguably one of the most important examples in the unit because it's basically encompassing all the stuff that we've done already. So in this example, we're given these three pairs of triangles, and we're said, can the given pairs of triangles be proven congruent with the information given in the diagram? And if so, which theorem could be used? So this is basically encompassing the stuff that we've done so far, and it's teaching us to read diagrams properly. Okay? Is there enough information? Is there not? Okay? And some are very tricky. And this is also an important thing. This is where it ties in some of the proofs that we've done, because these diagrams are pretty similar to some of the proofs we've done, where some information is given, some information is not, but we can pull it out just based on how the diagram is drawn. So, part A, we have these two triangles, right? My job is to say, can I show that this triangle is congruent to this other triangle, besides the fact that maybe they just look the same? Okay, I have to go deeper than that, and this is one of the things I have to use over here. So here's the spoiler alert. This first method, where I have to show all three corresponding angles and all three corresponding sides are congruent, you're not going to be using this. The reason why is that that's a lot of information, and the whole point of this unit was to show, like, all right, what are my shortcuts? So it's going to be one of these guys. All right. So let's look at what information was given in this diagram. I'm told that both of these angles, angle E and angle H, are right angles. Hopefully you can see that that's a little box. Sorry if I got sloppy with my writing. But these are 90-degree angles. So first off, I have an angle, right? But also I have a right angle, which just should, so you know, should set off like a red flag saying that, well, maybe HL theorem is up for grabs here. That doesn't mean I have to use it, but it means I can, because I have right triangles. The other piece of information I have is I have this side length DG being congruent to GF right here. So I have a side and I have an angle. Now, they didn't give me anything else, or at least tell me explicitly anything else with this drawing, but there is another thing I can pull out of here. So first off, let's just eliminate one of the ones that maybe you would have thought we'd be using simply because we have a right angle, HL theorem. in order to use this guy, I need a hypotenuse and a leg. Well, here's the good news. DG and GF are both hypotenuses. We know that because they're opposite the 90-degree angle. So I have the H, but I have no information about DH and no information about EF. I have no information about EG or GH. So there's no leg I can prove is congruent to another. Okay. In fact, if you were to claim like, well, yeah, it looks the same, I could actually redraw this with the same exact given information where it would look where you'd be able to see that there is no leg that can be drawn that way. Okay. But here is the major thing. This ends up being the reason why I can show these triangles are congruent, because in fact they are. And it has to do with this angle here and this angle here. This is a theorem that we've known for a while now, and it's worth writing down in the margin as one of those ones that pops up every once in a while that you don't really get told about all too often, but it's called vertical angles. EH and DF here make an X, meaning that the angles made by that X, the angles opposite each other, have to be congruent to each other. So angle DGH right here and angle EGF right here, they have to be congruent to each other because they're vertical angles. Why did that matter? Because now I have an angle congruent to an angle, I have an angle congruent to an angle, and a side congruent to a side. AAS ends up being this guy. So the real trick with this one was seeing that I have vertical angles created right here, and because of those vertical angles, now I can use AAS. A lot of people get tricked up by this right angle. They think that like, oh shoot, I have to use HL theorem. No, you don't have to. You can if you have enough information, but you don't have to use HL theorem. All right, part B. So here is a case, just let me distinguish between A and B right here. This is a case where I see that I have two triangles, this one on the left and one on the right, that share something in common. They overlap a little bit. They share this QM in common. We're going to actually use that in a second. Whereas this one, the only thing that they shared in common was this point G. That's not enough for me to get any side or angles. I can't use reflexive property in any way, shape, or form in this one. In this guy, I can use reflexive property. QM is part of both those triangles. And so QM has to be congruent to itself. So I have a side. I'm given that this side is congruent to that side. So I have two sides. But I have no information about any angles. I have no vertical angles. There's no X made here, right? So, and there's nothing saying, yep. So I have side between these two triangles right here. So I have no information about PM or MR. The one tricky part right here, and the reason I paused right there is because I was thinking about this, is that this is an isosceles triangle. The big triangle is an isosceles triangle. And by base angles theorem, what we did in section 4, angle P has to be congruent to angle R. That is absolutely true. But is that enough? I'd have A, S, S, and that would be spectacular if that were actually a theorem. However, it is not. And here's why. You can actually see on purpose, I drew this line a little bit off its grid line right here. So this triangle on the right side is a little bit thinner than this guy. And I could actually be a little bit more obvious about it and bend this segment QM more this way so you could see it. But quite obviously, the more I do that, this guy's definitely not congruent to that guy. And that's why ASS doesn't work, unfortunately. So this one is not enough information given in that diagram. Can they be proven congruent? No, not enough information for part B. Part C, this one I'm going to use reflexive property again. These two do share something in common, and now I do have information about angles. That angle is congruent to that angle, and this angle is congruent to that angle. So I have two angles, and this shared side, MP, is congruent to itself. Now I'm not going to get an ASS problem like I did over here. Instead I have A, S, A. By ASA, angle side angle, these two triangles have to be congruent to each other. So the tricky one here was the not enough info, but there you go.